Okay, now we're going to talk about the graphs of inverse trig functions. But before we actually get into the graphs of inverse trig functions, I wanted to do a quick review with you of what an inverse function is in general. So the whole idea of an inverse is when you switch the x's and the y. So the inputs and the outputs get switched. So, for example, if I have a function that looks like this, so this is the point 1, -2. This is the point 2, 0. This is the point 3, 2. And this is the point 5, 3. If I asked you to find the inverse of this function, literally what you are going to do is switch the x and the y coordinates and then regraph those points. So let's call this f of x in red, and I'll draw the inverse in blue. So on the graph of f of x, we have the point 1, -2, which means on the graph of the inverse, I would have the point -2, 1. On the graph of f, I have the point 2, 0, which means on the graph of f inverse, I would have the point 0, 2. On the graph of f of x, I have the point 3, 2, which means on the graph of the inverse, I would have the point 2, 3. And the last point we're going to plot, on the graph of f of x, we have the point 5, 3, which means on the inverse, I would have the point 3, 5. So then when I redraw this, I would have the inverse. And if you draw it accurately, I'm not the best artist, it should be a reflection across the line y equals x. So across the line y equals x, it should look like a mirror image. So the whole idea with inverses is you switch the x's and the y's, and because of that, the domain and range get swapped too. Because for the domain of f of x, that's the set of all x's, and the range of f of x, that's the set of all y's. So when they get swapped, the domain of f of x now becomes the range of f inverse, and the range of f becomes the domain of f inverse. Okay, now, there are times when you have to do what's called restricting the domain. If you want the inverse itself to also be a function, there are times where you have to restrict the domain of f of x in order for f inverse to be a function. So for example, if I graph our well-known function, x squared, this is definitely a function because it passes the vertical line test. However, if I look at the points on this, so we would have the point 0, 0, then we would have the point 1, 1, 2, 4, 3, 9, and then over here we would have negative 1, 1, negative 2, 4, and negative 3, 9. If I go ahead and graph the inverse of x squared, what's going to end up happening is that I'm going to get this picture. If I swap, let's go through and actually do that. If I swap the point 1, 1, I'm going to get 1, 1. If I swap the point to 4, I'm going to get 4, 2. If I swap the point 3, 9, I'm going to get 9, 3. And then if I swap the point negative 1, 1, I'm going to get the point 1, negative 1. So I'll get this point here. And then if I swap negative 2, 4, I'm going to get the point 4, negative 2. And then if I swap the point negative 3, 9, I'm going to get the point 9, negative 3. So as you can see, the inverse of f in this case is no longer a function because we have two y values for x is equal to 1. We have 1 and negative 1. We have two y values for x is equal to 4, and we have two y values for x is equal to 9. In fact, we have two y values for pretty much every point on that graph except for the point at x equals 0. So if we want the graph of the inverse to also be a function, we have to do what's called limiting or restricting the domain. So what we would do is we would cut off a piece of the original function f of x to make it a one-to-one function. So for example, I'm going to draw it in blue. We would only keep this part of the graph, and I would cross off and get rid of this other half on the left of 0. So I would say this is the graph of f of x, but with the restricted domain, and I'm only keeping the x's when x is greater than or equal to 0, and I would completely omit the left side of that graph from 0 to the left. And what would then happen is when I omit that left side of the graph, that gets rid of this bottom half down here that have the repeat x's with the negative values for y. And so then I would only have this half up here, and then when I draw vertical lines, it passes the vertical line test so that it would be a function. So that's what we're going to have to do with our trig functions, and we have to restrict the domain so that when we do the inverses themselves will also be a function. So if we look at the graph of sine x, it starts at 0, 0, it comes up to 1, then it comes down to negative 1, and then if we look at just the first cycle, then it stops at 2 pi here. But it keeps going, right? It goes on forever in either direction. If I want this to be a one-to-one function, I have to cut off and keep just a certain piece of the graph so that it's a one-to-one function. We can restrict the domain however we want, as long as it's a one-to-one function, but mathematicians and scientists like to be consistent and all agree upon how we're going to restrict the domain so that it makes everything a little bit easier. We're going to keep the part of the graph that goes from minus pi over 2 to pi over 2. So in blue, I'll write the part that we're keeping. We're keeping this part right here, where it goes from minus pi over 2 to pi over 2. By keeping just that part, we have now created a one-to-one function for sine. Okay, now the range is going to be, of course, negative 1 to 1. So now when we switch our x's and y's to get the inverse, so this point right here on sine is the point pi over 2, 1. This is, of course, 0, 0, and then this is, of course, minus pi over 2, negative 1. So now when we switch all those points, when we switch the x's and y's of those points to get the inverse, I now have the point on there, negative 1, negative pi over 2, which would be right here, then 0, 0, and then 1 pi over 2. So now it's going to look like this. That's what the inverse sine is going to look like. Now, I'm a horrible artist, and I'm not the best at scaling and making this as accurate as possible. But there is a sheet on Canvas that has really nice pictures with everything scaled and all the information on there as a reference sheet that I posted that you can print and look at and get a better picture of what that looks like. Okay, so for the inverse sine then, the domain is going to be negative 1 to 1 because all my x's and y's switch, and my range is going to be minus pi over 2 to pi over 2. And if we're looking at that in terms of the unit circle, that would be looking at quadrant 1 and quadrant 4 because minus pi over 2 comes out this way because it's a negative angle, and then pi over 2 comes up this way. So when we are simplifying expressions later using inverse functions, you want to keep in mind when you're dealing with sine, you're looking at quadrants 1 and 4. Okay, so the graph of the mother function for cosine looks like this. You have the point 0, 1. And then at pi over 2, it goes down to 0. And then at pi, it comes down to negative 1. And then at 3 pi over 2, it's 0 again. And at 2 pi, it comes back up this way. And then, of course, it repeats. Okay, for cosine, we restrict the domain to make it a one-to-one function so that it's from 0 to pi. We're keeping this piece and we're getting rid of everything else. So the restricted domain is going to be from 0 to pi. And of course, the range is negative 1 to 1. So we have the point on here, 0, 1, pi over 2, 0, and then pi negative 1. So when we switch our x's and y's then to draw the inverse, we have this picture. So we have the point 0, 1 on the mother function. So then we have the point 1, 0 on the inverse. On the mother function, we have the point pi over 2, 0. So on the inverse, we have 0 pi over 2. And then on the mother function, we have the point pi and negative 1. So then on the inverse, we have the point negative 1 pi. So the inverse will look like this. The domain of the inverse will, of course, be negative 1 to 1 because our x's and y's get switched. And the range of the inverse will be 0 to pi. So when you're looking at that on the unit circle and we're trying to evaluate expressions later that involve inverse cosine from 0 to pi, then we're dealing with quadrants 1 and 2 for cosine, for inverse cosine. Okay, for tangent, we have the point on there 0, 0. Then at pi over 4, we have the point 1. And then at pi over 2, we have an asymptote. And if we go in the other direction, pi over 4, x at negative 1, and then at negative pi over 2, we have another asymptote. And our graph of tangent looks like this. If we keep just this piece here between negative pi over 2 and pi over 2 is 1 to 1. Now if we continue and we look at the rest of tangent, it keeps going and repeats. But we only want to pick a piece of the graph so that it's 1 to 1. So scientists and mathematicians have agreed to restrict the domain so that it's from minus pi over 2 to pi over 2. And that way we get a 1 to 1 function. So when we take the inverse of that, then we get an inverse that is also a function. The range, of course, would be minus infinity to infinity. So we're only keeping this part that's in blue when we restrict the domain. Okay, now, because we have asymptotes on the mother function at x equals pi over 2 and x equals negative pi over 2, since our x's and our y's get swapped, now we're going to have asymptotes at y equals pi over 2 and y equals negative pi over 2. So the vertical asymptotes now switch to become horizontal asymptotes. Now if we start plotting points, we have a point on the mother function, negative pi over 4, negative 1. So when we swap that, we're going to have the point negative 1, negative pi over 4. And then switching 0, 0 remains the same. It's still 0, 0. And then if we switch the point pi over 4, 1, we get 1 pi over 4. So now our inverse looks like this. So it looks like the tangent function has gone sideways now rather than up and down. I'm not the best artist. This is supposed to flatten out here, come up through here, and then flatten out here. It doesn't look very good, but you can look at our reference sheet. It shows a much better picture. For cosecant, our mother function looks like this. It's undefined at 0. So for cosecant, it's undefined at 0, pi, 2 pi, any multiple of pi. And then when we graph it, it's going to look like this. This is what the mother function looks like. And it's just going to keep repeating. And this is at 1, and this is at negative 1. So when we restrict the domain for cosecant, scientists and mathematicians have agreed to be consistent and keep it from minus pi over 2 to pi over 2. So they're keeping this piece here so that it's a 1 to 1 function that I just highlighted in blue. So the restricted domain for cosecant will be from minus pi over 2 to pi over 2. But we can't write it down as one complete interval because there is an asymptotic 0 in there. So we're going to write it from minus pi over 2 to 0, union, we're going to skip over 0 and then goes to 0 to pi over 2. And then, of course, the range is from minus infinity up to negative 1, union, and then 1 to positive infinity. Because we have this blank space where there is no points in between 1 and -1. So now when we go to graph the inverse and we switch the x's and the y's, if we have the point on the mother function, -pi/2, -1, then on the inverse, we're going to have the point -1, -pi/2, which is right here. We have a vertical asymptote at x equals 0. So on the inverse, we're going to have a horizontal asymptote at y equals 0. So my graph is going to come up like this and flatten out at 0. Then on the other side, we have the point pi/2, 1. So now it becomes the point 1 pi/2, but it's got to flatten out at the asymptote, so the other side is going to look like this. And again, sorry guys, my artistic skills are awful. If you want to get a better picture of this, look at the reference sheet that is posted online. So my domain of the inverse is now going to be -infinity to -1, union 1 to infinity, because the domain and ranges get swapped. And then the range becomes -pi/2 to 0, union 0, pi/2. So when you're looking at the unit circle, we're going to be looking at quadrants 1 and 4 when we're dealing with cosecant. For secant, our mother function looks like this. We're going to have asymptotes at pi/2 and 3 pi/2, and then -pi/2, and our function looks like this. This is at 1, this is at -1, and it comes down like this, and then it repeats again. And then it keeps repeating on forever. For secant, we keep and we restrict the domain so that we keep this piece here and this piece here, so that it's a one-to-one function. So the restricted domain is going to be from 0 to pi/2. Skip over pi/2 because there's an asymptote there, and then pi/2 to pi. And then, of course, the range is -infinity up to -1, and then 1 to infinity, because we have that blank space in between here where there are no values for the function. Now when we graph the inverse, since we have a vertical asymptote at pi/2, on the inverse we're going to have a horizontal asymptote at pi/2. So it switches from x is equal to pi/2 to y is equal to pi/2 for my asymptote. Then when we start plotting points, on the mother function we have the point 0, 1. So we're going to have the point 1, 0 on the inverse function. And then it's got to flatten out at the horizontal asymptote. And we also have the point at pi/1 on the mother function. So we're going to have the point -1 pi on the inverse. And then it's got to flatten out at the horizontal asymptote. So this is what the inverse secant graph looks like. So the domain for the inverse is going to be from -infinity up to -1, and then 1 to infinity, because we have that blank space in between -1 and 1 for the domain. The range is going to be from 0 to pi over 2 union pi over 2 to pi. And then when we're looking at the unit circle, because we're looking at 0 to pi over 2 union pi over 2 to pi, that's going to be quadrant 1 and quadrant 2 when we're dealing with expressions with inverse secant in them. Okay, last inverse function, cotangent. For cotangent, we're going to have asymptotes at multiples of pi. And then at pi over 4, we're going to have 1, and then at 3 pi over 4, we're going to have the point -1. So it comes up like this. At pi over 2, it's 0. And then it comes down on the other side. On the left side of the asymptote at x equals pi is going to go down. And so it's going to continue to repeat like that, of course. And so mathematicians and scientists have agreed to keep this piece and restrict the domain from 0 to pi. So the domain for cotangent with the restricted domain is going to be 0 to pi. And notice that I don't include 0 and pi here because they're asymptotes. And of course, the range is going to be from -infinity to infinity. So now when we draw the inverse cotangent, since we have asymptotes at x equals 0 and x equals pi, we're now going to have asymptotes for the inverse at y equals 0 and y equals pi. And then when we switch our points, this is at pi over 2, this is at pi over 4, and this is at 3 pi over 4. When we switch our points, it's going to look like this. So now our inverse cotangent looks like it's on its side now instead of going up and down. So for the inverse cotangent, the domain is going to be -infinity to infinity, and the range is going to be from 0 to pi, not including 0 pi because there are asymptotes there and it never touches the line y equals pi and y equals 0. When we're dealing with expressions that have inverse cotangent, because we're looking at 0 to pi, we're looking at quadrants 1 and 2. Now that we understand the domain and range of our inverse trig functions, we can now apply that to evaluating expressions with inverse trig functions. So arc cotangent is just another way of saying inverse cotangent. And so when you're dealing with multiple parentheses, remember you always do the inside first. So cotangent of pi over 3. Cotangent of pi over 3, if we look at the unit circle, if we swing open to pi over 3, my terminal point is 1/2 and the square root of 3 over 2. Since cotangent is the value of x at that terminal point divided by the value of y at that terminal point, my ratio for cotangent at pi over 3 is going to be 1 over the square root of 3. So now we're looking for inverse cotangent. And don't forget, with inverse functions, remember you're switching your inputs and your outputs. So with inverse cotangents or any inverse trig function, what you're doing is you're getting out an angle, because normally with the mother functions, you plug in an angle and you get out a ratio. But when you switch the inputs and the outputs and you're looking at inverse functions, now you're plugging in the ratio and what you're getting out is an angle. So whenever you're dealing with inverse trig functions, your output should be an angle. So now with cotangent, our output should be an angle, but we specifically said for our range for cotangent, it should be in either quadrant 1 or quadrant 2 because we're going from 0 to pi. So in quadrant 1 or 2, where is cotangent 1 over the square root of 3? Well, that would be pi over 3. So our answer for this expression is pi over 3. Okay, so arc cosine of cosine of 7 pi over 6. So arc cosine is just another way of saying inverse cosine of cosine of 7 pi over 6. So when we look at the unit circle, 7 pi over 6 will give me an x value of negative square root of 3 over 2. So I'm replacing cosine of 7 pi over 6 with negative square root of 3 over 2. If we look at our range for inverse cosine, we should be looking at quadrants 1 and 2. So now this is asking, since this is inverse cosine, what angle would give me negative square root of 3 over 2? But remember, because of the restricted domains, we have to limit it to quadrant 1 and 2. So now I have to look at quadrant 1 and 2 and see where is cosine negative square root of 3 over 2. And that would be 5 pi over 6. Okay, this one is cosecant of arc cosecant, so inverse, negative 2 over the square root of 3. So we're going to do the inside first. So I'm going to replace cosecant, inverse cosecant of negative 2 over the square root of 3 with an angle, because remember, with inverses, we plug in the ratio and we get out the angle. So I got to figure out what angle goes in there and what I can replace inverse cosecant with. Well, for inverse cosecant, we have to look at quadrants 1 and 4. It's going to be between pi over 2 and negative pi over 2. So if I look at my unit circle and figure out where cosecant is negative 2 over the square root of 3, remember sine and cosecant are reciprocals. So really I'm looking to see where sine is negative square root of 3 over 2. And that would be at 5 pi over 3. Here's where it gets tricky. 5 pi over 3 is not in the range of cosecant. Remember, cosecant, the range has got to be from minus pi over 2 to pi over 2, except for 0, of course, because that's where we have an asymptote. So we've got to find the angle that's between minus pi over 2 and pi over 2. 5 pi over 3 opens this way because it's positive. So that's going to be, if we want to write it so that it's between minus pi over 2 and pi over 2, we got to write it as a negative angle. So we're going to write 5 pi over 3 as negative pi over 3. It's still coterminal, it still lands in the same spot, but 5 pi over 3 is not on that interval. We got to write 5 pi over 3 as negative pi over 3 so it fits on that interval. Now I'm going to take the cosecant of negative pi over 3, and the cosecant of negative pi over 3 would be the reciprocal of sine at negative pi over 3, and sine at negative pi over 3 is negative square root of 3 over 2, so this is going to be negative 2 over the square root of 3 as our final answer. So these can be tricky because you really have to pay attention to what quadrant you're in, what interval you should be on, and if you're plugging in a ratio or if you're plugging in an angle. So you really got to keep track of what you're doing. Okay, so we're going to do sine and then inverse sine of square root of 3 over 2. So with inverse sine, we should be getting out an angle. So I should be putting in an angle in here. With sine, remember we're dealing with quadrant 1 and quadrant 4, and it's got to be between negative pi over 2 and pi over 2 except for 0 because that's where the asymptote is. So if we look at the unit circle and we look to see where sine is positive square root of 3 over 2, that would be at pi over 3, and that falls in quadrant 1. And then if I take the sine of pi over 3, I get the square root of 3 over 2. So there's my final answer. So for this example here, we have cotangent and then inverse sine of negative 1/3. And remember, because this is inverse sine, that represents an angle. So I'm going to take cotangent of some angle. Well, that negative 1/3 is not on our unit circle. It's not one of our key angles. So we're going to have to use a triangle to figure this out. So I'm going to label theta as this angle here. And sine is opposite over hypotenuse. So this is going to be 1 and this is going to be 3. Keeping in mind that this angle has to be in the 4th quadrant. Because remember, when we're dealing with inverse sine, we're dealing with quadrant 1 and quadrant 4. And sine isn't negative in the 1st quadrant. It's negative in the 4th quadrant. So that angle is going to be in the 4th quadrant. Okay, so let's see. If I use Pythagorean theorem, I'm going to find that the other leg is going to be 2 square roots of 2. And cotangent is adjacent over opposite. So cotangent is going to be 2 square roots of 2 over 1. And also because it's in the 4th quadrant, we know that cotangent is negative in the 4th quadrant. So my final answer has got to be negative 2 square roots of 2. This is going to be an angle because it's asking for an inverse of a ratio. So we're going to get out an angle there. Since we're dealing with sine, we're going to be looking at the 1st and the 4th quadrant. So it's got to be between negative pi over 2 and pi over 2, except for 0 because that's where our asymptote is. So I got to look in the 4th quadrant and see where sine is negative 1/2. And sine is negative 1/2 at 11 pi over 6. However, that is not an angle that's between negative pi over 2 and pi over 2. So I have to rewrite it as a coterminal angle as minus pi over 6 so that it fixed that, so it satisfies that requirement of falling between negative pi over 2 and pi over 2. So I'm going to rewrite this as cosine of negative pi over 6. And then I'm going to take the cosine of negative pi over 6, and that is the square root of 3 over 2. Okay, in example 7, it says, write cosine of sine inverse of x as an algebraic expression in terms of x. So remember, this represents an angle because it's an inverse trig function. Right? With inverse trig functions, we plug in the ratio, we get out the angle. So I'm going to use the triangle method to set this up. So since sine of theta is equal to x over 1, if we rewrite that, then, and sine is opposite over hypotenuse, I can find this other leg by using Pythagorean theorem. So it would be 1 minus x squared and then take the square root. Now, I want to find cosine of that angle. So cosine is adjacent over hypotenuse. So adjacent over hypotenuse is 1 minus x squared all over 1, which is just 1 minus x squared. Okay, we're going to do the same thing for this last example. This represents an angle. So we can write this as tangent of the angle is x over 1. So here's my angle. Tangent is opposite over adjacent. So using Pythagorean theorem, I can find that it's the square root of x squared plus 1 as my hypotenuse. And then I want to find secant of that angle. Secant is hypotenuse over adjacent. So that is x squared plus 1 all over 1, which is x squared plus 1.